Class 11 Mathematics, NCERT New Delhi and COHSEM Manipur. Unit 2 Algebra. Topic Complex Numbers and Quadratic Equations. Subtopic Need for complex numbers, the fundamental imaginary unit or small I. Complex numbers in the form of a plus ib, algebra of complex numbers. Real and imaginary parts of a complex number, complex conjugates. Exercise 5.1. Complex numbers and quadratic equations. Complex number. A number of the form a plus ib where a and b are real numbers and small I equal to square root of minus 1 is called a complex number. A plus ib की form da a amasung b na real number sing oiba I na square root of minus 1 oiba number amabu complex number kawi. For the complex number z equal to a plus ib, z na represent riba complex number asigi. A is called the real part denoted by re of z, real part of z aina pagani, and b is called the imaginary part denoted by im of z, imaginary part of z of the complex number. Z equal to a plus ib da a asibu real part of z masibu re of z na khangnagani paba matamda real part of z aina pagani. B asibu na imaginary part of z masibu im of z haigani paba matamda di imaginary part of z haigani. The set of complex numbers is denoted by capital C. Thus, C equal to set of all z such that z equal to a plus ib, ab belongs to r, and I equal to square root of minus 1. Two complex numbers z1 equal to a plus ib and z2 equal to c plus id are equal if a equal to c and b equal to d. हाइबदी रियल गा लोइनना इमाजिनरी पार्ट का मानरबदी complex number ani do manaba complex number sing. Algebra of complex numbers. Z1 plus Z2 complex number ani se Z1 sin a plus ib ga manahal si Z2 c plus id ga manahal si sigumba complex number ani sum di like terms a ga siga a plus c phange plus I yawa term ani di I kamal logto crop b plus d. A plus c se real number ni, b plus d su real number ni, which is in the form of a plus ib. Therefore, this number belongs to c. However, the sum of two complex numbers is again a complex number. Z1 minus Z2, a plus ib minus c plus id. I yaudaba tam ani si a minus c phange, I yaudaba tam ani sregi I kamal logtokrabadi we get a plus I times of b minus d, which is in the form of a plus ib. Therefore, this belongs to C, the set of complex numbers. Subtraction of two complex numbers is always a complex number. 3. Z1 into Z2. Z1 is represented by a plus ib, Z2 is C plus id. Actual multiply tarabadi we get new real part to AC minus BD plus I times of AD plus BC, which is also in the form of a plus ib. Therefore, this new number belongs to C, the set of complex numbers, from which we learn that product of two complex numbers is again a complex number. 4. Z1 divided by Z2. Z1 is equal to a plus ib, Z2 is C plus id. Multiplying on numerator and denominator by c minus id, we get this. New real part is this, new imaginary part is this, which is in the form of a plus ib. Therefore, this new number belongs to C, the set of complex numbers, where Z2 plus Z2 is equal to C plus id does not equal to 0. Thus, from which we learn that quotient of two complex numbers, where denominator does not equal to 0, is again a complex number. 3. The addition of complex numbers satisfy the properties. Complex numbers tinsinabana makhagi property magul singasi chumi. The closure property haibadi z1 plus z2 belongs to C. The sum of any two complex numbers is again a complex number. This property is known as closure property over addition. The commutative property, that is z1 plus z2 equal to z2 plus z1. Addition of any two complex numbers is independent of order. Order gi makha ponde. This is known as closure property. 3. The associative property, z1 plus z2 plus z3 equal to z1 plus z2 plus z3. The sum of three complex numbers is independent of the grouping. Complex number ahum tinsinabasi group ki makha ponde. This law is known as associative property. The existence of additive identity element. Additive identity element laiba. Z1, any complex number plus 0 is again Z1. 0 is called additive identity element. Z, any complex number 0 haiba complex number sum up torabadi any complex number tai. Mafam asida 0 asibu kari kawe additive identity element kawe. Next, the existence of additive inverse. Additive inverse laiba. Z1 plus minus Z1 equal to minus Z1 plus Z1 equal to 0. Z1 ga minus Z1 ga sum up any order the sum up to 0 tai. Minus Z1 asibu Z1 gi additive inverse kawi or Z asibu minus Z1 gi additive inverse kawi. The multiplication of complex numbers satisfy the properties. Complex numbers sing puri nabada makhagi gul singa chichume. The closure property haibadi z1 into z2 belongs to C. The multiplication of two complex numbers is again a complex number. This law is known as closure property on a multiplication of complex numbers. Next, the commutative property z1 into z2 equal to z2 into z1. The multiplication of two complex numbers is independent of independent of order. The associative property z1 into z2 z3 equal to z1 into z2 times of z3, which law states that multiplication of three complex numbers is independent of grouping. The existence of multiplicative identity element z1 into 1 is z1. Any complex number, the product of any complex number with 1 is any complex number. Here 1 is called multiplicative identity element. The existence of multiplicative inverse z1 into 1 by z1 is 1. 1 by z1 asibu z1 gi multiplicative inverse kawi. The distributive law 1. Z1 times of z2 plus z3 is equal to z1 into z2 plus z1 into z3. 2. Z1 plus Z2 times of Z3 is equal to Z1 Z3 plus Z2 Z3. Note, the multiplicative inverse of Z1 equal to A plus IB is A by A square plus B square plus I times of minus B by A square plus B square. Remember this formula. The multiplicative inverse of this complex number is this. Remember this. Powers of I. I means square root of minus 1, whose power is 4n, which become 1. I power 4n plus 1 is I power 4n plus 2 is minus 1. I power 4n plus 3 is minus I, where n is any integer. The square roots of a negative real number. The square root of a negative real number is called an imaginary number. Is the square root of minus 1, square root of minus 2, square root of minus 5, etc. They are called imaginary number. That is, the square root of a negative real number is called imaginary number. If a is a positive real number, square root of minus a is an imaginary number which can be written as square root of a into square root of minus 1. Square root of minus 1 can be represented by I, from which we learn that any imaginary number can be expressed as product of two numbers. One is real number, another one is I, fundamental imaginary unit. If a and b are positive real numbers, square root of minus a minus a into square root of minus b. Product of two imaginary number is, already learned that square root of minus a can be put square root of a into I. Square root of minus b also can be put in square root of b into I whose square is minus 1. We get minus root over square root of ab. Identities. Z1 plus Z2 whole square is equal to Z1 square plus twice of Z1 Z2 plus Z2 square. Z1 minus Z2 whole square is equal to Z1 square minus twice of Z1 Z2 plus Z2 square. 3. Z1 plus Z3 whole cube is Z1 cube plus 3Z1 square into Z2 plus 3Z1 into Z2 square plus Z2 cube. Z1 minus Z2 whole cube is Z1 cube minus 3Z1 square into Z2 plus thrice of Z1 into Z2 square minus Z2 cube. Z1 square minus Z2 square is Z1 minus Z2 times of Z1 plus Z2. The modulus and the conjugate of a complex number. The modulus of a complex number Z equal to A plus IB denoted by Z with single bar taken par. We have to read it as modulus of Z is the quantity square root of A square plus B square. Thus, modulus of Z equal to modulus of A plus IB is equal to square root of A square plus B square. That is square root of real part ki square plus imaginary part ki square. The conjugate of a complex number Z equal to A plus IB denoted by Z with single bar taken bar is A minus IB, which is obtained by changing the sign of the imaginary part. If it is plus B, it should be minus B. Thus Z bar conjugate of Z is equal to A minus IB. Important reasons. Modulus of Z1 into Z2 is the product of moduli of the complex numbers. Modulus of the quotient of two complex numbers is equal to modulus of numerator by modulus of denominator. 3. Conjugate of the product of two complex numbers is the product of the conjugates of the complex numbers. 4. Conjugate of the Z1 plus Z2 is equal to conjugate of Z1 plus conjugate of Z2. Conjugate of Z1 minus Z2 is also equal to conjugate of Z1 minus conjugate of Z2. Conjugate of Z1 divided by Z2 is equal to conjugate of Z1 by conjugate of Z2. Z into its conjugate equal to square of its modulus. Exercise 5.1. Express each of the complex number given in the exercises 1 to 10 in the form A plus IB. Makhada piriba complex number singasi A plus IB gi form the phongdu u. For 1, 5I into this, we have to multiply 5 into minus 3 by 5. Firstly, that is minus 3. I into I is I square. We have learned that I square is minus 1. Therefore, minus 3 into minus 1 is plus 3, which can be expressed in the form of 3 plus I times of 0, where imaginary part is 0, which is in the form of A plus IB. For Roman number 2, I power 9 plus I power 19. Express I power 9 in terms of I power 4. I power 4 into whole square into I plus I power 19 is I power 4 whole to the power 4 into I cube. I power 4 is 1 whose square is 1 into I power 4 is 1 whose power is 4 into minus I cube is minus I. We get I minus I, which is 0, which can be put in the form of 0 plus 0I. For 3, I power minus 39, which can be written as I power minus 40 plus 1. I power minus 40 can be written as I power 4 whole to the power minus 10. I square remains unchanged. I power 4 is 1 whose power minus 10 is 1, and 1 into I is I, which also can be put in the form of 0 plus I. Here real part is 0. For 4, we have to multiply 3 into 7 is 21. 3 into 7 is 21 times of I plus I into 7 is 7I. Plus I square is minus 1 minus 7. Sum of 21 minus 7 is 14. Plus 21 I plus 7i is 28i, which is in the form of a plus ib. For 5, 1 minus I minus 1 minus 1 plus 6i. Open the bracket, we get this, which is in the form of 2 minus 7i. Express the each of the complex number given in the exercises 1 to 10 in the form a plus ib. For question number 6, open the bracket, and combine the real parts as well as real parts. We get this, sum up, we get minus 19 by 5 minus 21 by 10 times I, which is in the form of a plus ib. For 7, we have to open, sum up the real, combine the real parts and combine the imaginary parts, that is the term containing I. We get this, simplify. Lastly, we get 17 by 3 plus 5 by 3 times of I, which is in the form of a plus ib. For question number I, 1 minus I, which can be expressed 1 minus I whole cube into 1 minus I. 1 minus I whole cube whose expansion is this, and 1 minus I remains unchanged. Simplify the bracket, first bracket, we get this, again simplify, we get minus, taking out minus, multiply by minus 2 in each term, we get this, and by minus 2i we get this. Combine, we get minus 4 plus 0i, which is in the form of a plus ib. For 9, we have to expand using the formula a plus b whole cube, we get this. Simplify 1 by 27 whose square cancelling, we get I. For this we get minus 9. For this we get minus 27i. Combine two real numbers and the two terms containing I, we get this, and again simplify, we get this, which is in the form of a plus ib. For number 10, taking out minus from power cube, we get minus times of 2 plus I by 3. Expand using the standard formula a plus b whole cube, we get this, and simplify, we get this, and which is also in the form of a plus ib. Find the multiplicative inverse of each of the complex numbers given in the exercise 11 to 13. Complex number single multiplicative inverse put to hyphen 11. The multiplicative inverse of 4 minus 3i is 4 plus 3i divided by 4 square plus 3 square, that is 25. 4 by 25 plus 3 by 25 times of I, using this formula. For 12, the multiplicative inverse of this is using this formula, we get, whose value z bar is this, and modulus of z square is this, and simplify, we get root over 5 by 14, which is the real part. Imaginary part is minus 3 by 14 times of I. For 13, the multiplicative inverse of minus I is I by 1 square, which is I. Express the following expression in the form of a plus ib. Expand, simplify, which is a plus b whole into a minus b. Applying that formula, we get a square is 3 square minus b square is I times of root over 5 whole square. Then expand the denominator and evaluate, we get cancelling root 3 minus root 3, we get, which is minus into minus is plus, we get 2 times root over 2i, we get 9 plus 5, I square is minus 1, that makes plus root over 5 square is 5, we get this. We have to put in the form of a plus id. 0 minus 7 root over 2 by 2 times of I, which is in the form of a plus ib. Thank you for watching video.